All right, now I want to talk about a different complexity class, a class of decidable languages that we think might be a little bit broader than the class P, although it's never been proved and it's actually an open problem as to whether this is broader than P. And so on the front page of our theory webpage, I actually have a little picture from my computer science undergrad building in Princeton, where they have etched in that question, whether P and NP are actually the same complexity class. So I'll define NP in a moment, but I actually want to show you first a problem that is in NP that we think might not be in P if they're different. So somehow this is a problem. NPs we think might have some problems that are a little bit harder that maybe can't be solved in polynomial time, but we're not sure. This is possibly one of them. So it's something called a Hamiltonian path. So a Hamiltonian path is with respect to a graph. So given a graph G, which it can be written as a two-tuple, it's just a set of vertices and a set of edges. So the vertices here I've depicted as dots in this example, and the edges are lines between them. So given a graph, a Hamiltonian path is a permutation of the vertices, so that each adjacent pair of vertices in the permutation is connected by an edge in the graph. All right, so that is the definition of a Hamiltonian path. And so as an example, in this graph that I've given, a Hamiltonian path would be the permutation 2, 0, 1, 6, 5, 3, 7, 4. So let's see why. If I look at that, okay, so 2, 0, 0, 1. So I'm just making sure these are in the graph. 2, 0, 0, 1, 1, 6, that was in the graph. 6, 5, 5, 3, 3, 7, and 7, 4. So let me highlight that path in red here. So there is the Hamiltonian path. And maybe I'll draw it as a dotted line so we can see that the original edges are still there. So there's my Hamiltonian path. So one way to think about a Hamiltonian path, it's a way to draw a path through the graph, through the edges that are there, so that you visit each vertex exactly once. And you're able to visit every vertex this way without revisiting something that you've already visited. So I always like to define it using a permutation because that automatically captures the fact that we never repeat a vertex. So there's a Hamiltonian path. Now if I wanted to turn this into a language, I would say, this is the set of G, and then maybe I'll say P, where P is a permutation, given that G is a graph and P is a Hamiltonian path. Whoops. And P is a Hamiltonian path with respect to G. So in this case, this graph, you could certainly encode this as a string. It would just be we don't care about position, we just care about connectedness information here. So I could just encode V as a tuple of 0, 1, 2, 3, 4, 5, 6, 7, and then I could encode the edges as a tuple of pairs of vertices. So the string encoding of the graph and the encoding of this permutation of the vertices is in the language of Hamiltonian paths if G is a valid graph and this P is a Hamiltonian path with respect to G. So this, the above G and this permutation is in the language. But, this encoding G, if I were to say 0, 1, 2, 3, 4, 5, 6, 7, is actually not in Ham path. Because if I look at this, sorry, I keep putting my head over this stuff. But yeah, so if I tried to go through the vertices in the order that I've labeled them here, I would find that 0, 1, 2, 3, 4, 5, 6, 7 is not in there because the edge 4, 5 is not there and the edge 6, 7 is not in the graph. So that is not a valid Hamiltonian path. Okay, so I actually just demonstrated all the ingredients that we need to define NP. So let me now go ahead and do that. So I'm going to define languages a slightly different way, given two things. So number one, I'll say given a verifier V, which is a Turing machine. And so really we can think of it like an algorithm by the Church-Turing thesis. And a certificate called C, which is a string. So given a verifier V, which is a Turing machine, and a certificate C, we can define a language as follows. So a language is the set of all strings W, given that there exists a certificate, so that the verifier accepts WC, those two strings together. All right, so this is a formal way of saying the following. So intuitively, the verifier, or intuitively, the certificate is the solution to generating a string, or generating a solution to the problem that W represents. So here W was, the graph VE, right? So that would be like the string input to our Hamiltonian path decider if we were trying to decide this language. And we're trying to figure out if there exists a Hamiltonian path. And so if there does, then I should be able to give you a certificate. In this case, the certificate is the permutation. And the verifier is what goes through and does what I did, which is, okay, you gave me this permutation, this certificate. I'm going to verify that that actually is a solution to the input W here. So actually a solution to the Hamiltonian path on this graph. I'm going to verify that simply by checking to make sure, first of all, it's a valid permutation, right? So actually each element shows up exactly once. And then by walking through the graph and making sure that each adjacent pair is actually an edge in the graph. So that is my verifier. So it verifies the permutation, and then it goes through and makes sure that each adjacent pair in the permutation is actually an edge in the graph. So I need the graph. I need to feed the graph W, in this case. I need to feed the graph and the certificate to the verifier, and then the verifier can look at the graph and the certificate and say, oh yeah, that's a solution. And so I say you're in the language if I can actually find such a certificate. If I tweak this graph a little bit and I deleted certain edges, so let's say I deleted, maybe I made 7, just kind of for a trivial example, I made 7 off on an island by itself here. Well, then I could never find a certificate that would work because I would never be able to connect 7. 7 has to be in the permutation. I would never be able to connect 7 there. All right, now that we have that example under our belt, let's formally define NP. So NP is the set of all languages given that L can be verified in polynomial time. So it means that we can construct a Turing machine V, a verifier, that is able to verify. So more precisely, there exists a verifier V, so that for every certificate and string pair, the verifier, and I should say, of length n. So together, the certificate and the string input to the language are of length n. So there exists a verifier so that the verifier decides CW in polynomial time, where p is greater than 0. So that's the slightly more precise way of saying it. So NP is the set of all languages so that the language can be verified in polynomial time. That just means that I can construct a verifier so that it can decide whether a certificate actually has addressed and solved this problem W in polynomial time. So in my Hamiltonian path, I certainly can construct a polynomial time verifier. I don't even have to be particularly careful about my data structures I use, but let me write some pseudocode here. So here's my verifier. So, maybe it takes in some graph and the certificate, right? So actually, maybe I'll say the graph is G, and then I'll unpack the vertices and edges. And so what I would do is I would say, okay, I'm going to assume that you are a Hamiltonian path. So I'll say maybe is valid starts off as true. And what I'll do is I'll go through, so my certificate is a permutation. So I'll say for I in range length of C minus 1. And I'll pull out the two vertices. So I'll say, my first vertex U is equal to C at index I. My second vertex V is equal to C at index I plus 1. And I want to verify that UV is an edge. So I will just check. And I'll say, I'll start off by saying is an edge is false. And then I'll say for, my edge E in all the edges, I'll say if UV is that edge E, then I found it. It's a valid edge. So at the end here, I'll say if not is edge. So if I was not able to find this edge, then is valid is false. And so at the end, I'll just, if is valid, then we'll accept. Otherwise, we'll reject. So I claim this is a polynomial time verifier. So I say, let's just say given V vertices and E edges, well, this loop goes through big O of V steps, and this loop goes through big O of E steps. So the whole loop goes through, so the whole thing is big O of E times V steps. And, well, okay, so N is the length of the string encoding of the graph and the string encoding of the certificate, which is certainly upper bounded by E and V. So this is about, if I'm being very rough here, this is certainly upper bounded by big O of N squared, which is polynomial. So P equals 2. Great. That's polynomial. So that's great. I was able to come up with an algorithm that was polynomial time to verify that. Let me show you one more example, something called independent set. So here's a graph, and I'll show you independent set here. So the definition of independent set is given a graph, again, so given a graph is a tuple of vertices and edges. An independent set, let me make this just a little bit bigger. Independent set of size k is a subset X of vertices of length k, so that no pair of vertices in X is connected by an edge in E. So that's the definition of an independent set. So let me construct, I will construct an independent set of size 6 on the graph to the left. And so my certificate is going to be the set, I'll just write it down here, 0, 2, 4, B, D, E. So let me highlight those vertices here and show you that they make an independent set. So 0, 2, 4, B, D, oh, I meant to say B, D, F. Okay, let me change that to B, D, F. So I have these vertices, and I see that no pair of them is connected by an edge. And so I just visually showed you the verifier, but then how would I implement that in a little more detail at a high level? So my independent set verifier, so I have to specify this parameter k. my independent set verifier will go through, so I'll unpack the vertices and the edges again. And so my C is really my set of vertices, so I'll just go through each pair. So I'll say for x, y, or for u, v in C cross C, so that's the Cartesian product, right? So go through every pair of vertices in the certificate. And now I'll go through each edge. So again, I'll say for E in edges, if UV is E, so maybe I'll start off by saying is valid, is true. But if I find an edge that connects two of the vertices in my certificate, then I'm not valid. And so at the end, I'll just return is valid. So let's look at the time complexity. This is going to be go through big O of k squared iterations. This is going to go through big O of e iterations. And so overall, so given v vertices and e edges, the whole thing goes through big O of k squared times e steps, which, okay, so k could be on the order of n. So noting that k could actually be, so in this example, k, n was the number of vertices was 12, and k was 6, so half that. So k could actually be on the order of n. So if I want to be super careful here, I'll say that this is an big O of n cubed verifier. But that's fine. I'm just trying to show that it's a polynomial time verifier. All right, so we've seen the definition of MP. I've showed you a couple problems that are in MP. And let's just take a breath for a moment. And I'm going to make another video talking about the relationship between P and NP.